Go to your kitchen. Turn on the tap. Just a little. The water comes out in a smooth, clear ribbon. It looks almost solid. You could practically photograph it and hang it on the wall. A perfect glass column falling down into the sink. Now turn the knob a little more. And a little more. Watch what happens. At some moment, you can see it with your own eyes. That beautiful ribbon breaks up. It starts wiggling. It twists. It hisses. It turns into a jumbled, frothing, chaotic mess. The glass column shatters, right there in front of you. I want to tell you something that might surprise you. That thing you just watched, that little kitchen drama, is one of the great unsolved problems of physics. Not kind of unsolved, not mostly unsolved, unsolved. If you came to me and you said, Feynman, I have a pipe and water is running through it, and I want to know exactly when it will go from smooth to chaotic, and what pattern of swirls it will make, and where each little whirl will be at each moment, I would have to look at you, and I would have to tell you the truth. I cannot do it. Nobody can. You might think, well, surely the physicists have bigger fish to fry. Black holes, the inside of atoms, the origin of the universe. Why would anyone worry about water from a tap? Because here is the embarrassment. We think we are so smart. We have equations for quarks. We have theories that predict the behavior of galaxies. We can calculate certain properties of the electron to 10 decimal places. And yet something you can make with a garden hose in your own backyard, something you watch every time you wash your hands, defeats us utterly. This thing has a name. We call it turbulence. And today, I would like to take you with me on the hunt. Because the story of turbulence is the story of the smartest people in physics. For a century and a half, banging their heads against a wall. And that wall is still standing. So let us start at the beginning. What do we actually know? Here is the comforting part. For smooth, slow flow, the boring kind, where water goes gently through a pipe or honey drips off a spoon, we have got it. We really do. We solved that problem a long time ago. Picture honey dripping. Picture molasses in January, as people used to say in New England. The stuff barely moves. When it does move, it moves in neat, orderly layers. Each layer slides past the next like the pages of a book being fanned. The layer touching the walls of the jar barely moves at all. The layer in the middle moves the fastest, and every layer in between knows exactly what to do. We have a word for this kind of flow. We call it laminar, from the Latin word for thin sheets, because that is what it looks like. Thin sheets of fluid sliding past each other, very politely, very cooperatively. For laminar flow, everything works. We can predict the velocity at any point. We can calculate the pressure at any point. If I tell you the shape of the pipe, and the thickness of the fluid, and how hard you are pushing, I can tell you exactly what the flow looks like. Not approximately, exactly. It is a solved problem. The equations work. The predictions match the experiments. We put the thing to bed in the 1800s and went home. And for a long time, people thought all of fluid mechanics was like this. They thought if you could do laminar flow, you could do everything. Just crank the speed up or change the pipe, and the same equation should handle it. They were wrong. Spectacularly wrong. Because something weird happens when you push fluids harder. They stop being polite. They stop sliding in neat layers. They start doing something else entirely. There was a man named Osborne Reynolds, an engineer in England, late 1800s. He was curious about this problem. When does smooth flow go bad? So he built a clever little apparatus, a glass pipe, water flowing through it. And here is the genius move. He injected a thin stream of colored dye into the water, right at the mouth of the pipe. So now you have got clear water flowing, and inside that clear water a thin ribbon of color snaking its way down the glass pipe. You can see what the flow is doing. At slow speeds, pure poetry. The dye ribbon goes straight down the middle of the pipe, does not wiggle, does not spread. A perfect colored thread hanging in the water like a pencil line. laminar. Beautiful. Now Reynolds turns up the speed. Just a touch. The ribbon still holds. Still straight. A touch more. Still straight. A touch more. And suddenly, bang, the ribbon explodes. It bursts into a cloud of color that fills the whole pipe. It mixes, it churns, it does 1,000 things at once. Turbulent. Here is what got physicists excited. Reynolds did this experiment with different fluids. Water, oil, glycerin, different pipes, wide ones, narrow ones, different speeds. Every time at some moment the ribbon would break. And he noticed something marvelous. There was a number you could calculate from the speed and the width of the pipe and the thickness of the fluid. And when that number was small, the flow stayed smooth. When the number got big, the flow went chaotic. And the transition happened at just about the same number, every time, regardless of what fluid you used or what pipe you used. We call it the Reynolds number in his honor. It is basically a ratio. On the top, you have got the pushing forces, the inertia that wants to keep the fluid moving in a jumble. On the bottom, you have got the gentling forces, the viscosity that wants to smooth everything out. When inertia wins, chaos. When viscosity wins, calm. Think about it like this. Imagine you are in a crowd. If the crowd is small and you push one person, that person just bumps into the next, who sort of absorbs it and carries on. Everybody stays calm. But if the crowd is big and moving fast, and you push one person, that push ricochets. The person you pushed knocks into 3 others, who knock into 9, and suddenly the whole crowd is swirling around you. That ratio of how forceful your push is versus how much the crowd can absorb, that is a Reynolds number for crowds. So that is something, is it not? We have got a magic number. We know when the flow will change its character. But notice what we do not know. We do not know why. We do not know the mechanism. We do not know what is actually happening when that dye ribbon bursts. We just know that it does. Which is a bit like saying, well, I know the light goes on when I flip the switch, but I have no idea how electricity works. That is not really understanding, is it? All right, let us try to get at the mechanism. What do we have to work with? We have equations, very famous equations, developed in the 1800s by a Frenchman named Navier and an Englishman named Stokes. We call them the Navier-Stokes equations, and they are, in principle, the whole story of how fluids move. Any fluid, any shape, any speed, water, air, syrup, blood, whatever you like. They just say, Newton's second law, applied to a tiny blob of fluid. Force equals mass times acceleration, for the blob. The forces are pressure differences pushing the blob around, and viscosity dragging on it, and gravity, and whatever else. And the acceleration of the blob depends on how it was moving before. Sounds simple. Sounds like we should be done. Here is the trouble. Buried inside those equations is a term, a little piece of math, that says the way the fluid moves here depends on the way the fluid is moving, times the way the fluid is moving. The velocity multiplied by itself. Now this may not sound like a big deal, but in mathematics there is a word that should make every physicist shudder. The word is nonlinear. When you have got velocity multiplied by velocity, you have got nonlinear. And nonlinear equations are a different animal altogether. Let me tell you what linear means first, so you can feel the contrast. Linear is polite. Linear is cooperative. If you have got a linear system and you double the input, you double the output. If you push twice as hard, you get twice as much. If 2 waves meet, they just add up cleanly and pass through each other and go on their way. Linear problems we have tools for. We can break them into pieces, solve each piece, add the pieces back together. Works every time. Nonlinear is none of that. In a nonlinear system, if you push twice as hard, you might get 10 times as much. Or nothing. Or the opposite. 2 effects meeting do not just add up. They interact, they multiply, they create whole new effects that were not in either one alone. A nonlinear system can do things that nothing in it could do individually. And here is the horrible part. Nonlinear equations in general cannot be solved with pencil and paper. There is no formula. There is no tidy answer. You have to attack them numerically using machines, and even then you have to be very careful, because a tiny error in your calculation can blow up into a huge error in your answer. So when Reynolds's dye ribbon burst into chaos, what was actually happening? The Navier-Stokes equations were still running, the fluid was still obeying them, but the nonlinearity was now in charge. Every little wiggle in the flow was feeding other wiggles, and those wiggles were feeding more wiggles, and everything was shoving everything else around in ways that pencil and paper could not keep up with. We had the equations, we just could not solve them. It was like a detective who has the murder weapon, the fingerprints, the motive, and the opportunity, but somehow still cannot name the killer. All the evidence is sitting on the desk, he just cannot put it together. So we have our mystery. The equations work, but we cannot solve them. The Reynolds number tells us when chaos appears, but not why. We need more clues. Enter a fellow named Louis Fry Richardson, English mathematician, around the 1920s. Now Richardson had a peculiar obsession. He wanted to predict the weather. Weather, of course, is just turbulence in the atmosphere on a vast scale. Wind eddies, storm systems, the whole business. And Richardson, in trying to wrap his head around it, came up with a picture, a way of seeing what turbulence actually is. He put it into a little poem, which I will paraphrase for you, because I think it is one of the great pieces of physics poetry. Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. That is it. That is the whole picture. What does it mean? Imagine a big eddy in a river, a nice fat rotating patch of water. Now if you look closely at that big eddy, you see that it is not smooth. There are smaller eddies living inside it, feeding off the motion of the big one. And if you look inside those smaller eddies, you find even smaller ones, and smaller still, and smaller still. Turbulence, Richardson realized, is not one thing. It is a cascade. Energy gets pumped in at the largest scale, say a fan pushing air across a room, or wind blowing across a lake, and that energy starts in the biggest eddies. Then those big eddies break up into medium eddies. The medium eddies break up into smaller eddies. The smaller eddies break up into still smaller ones. And this continues down and down and down across a huge range of sizes, until finally you get down to eddies so small that viscosity, the molecular stickiness of the fluid, can grab them and dissipate them into heat. The motion stops being motion and becomes jiggling of atoms. Warmth. So turbulence is energy pouring down a waterfall of scales, from the big to the small, from order to disorder, from kinetic energy to heat. This is a beautiful picture. But look what it tells us about our problem. Turbulence is not a single phenomenon happening at one scale. It is a phenomenon that couples every scale together. The biggest eddies, the medium eddies, the tiny eddies, they are all talking to each other, all passing energy down the chain. If you want to describe the flow, you have to describe it at all scales at once. That is why the math is so ruthless. You cannot zoom in on just the big picture because the little picture is affecting it. You cannot zoom in on the little picture because the big picture is driving it. Everything is tangled up with everything else. There is no cleanest piece to grab. Around the same time, another marvelous thing happened in Germany with a fellow named Prandtl. Ludwig Prandtl. He was worried about a specific problem, about what happens to fluid right next to a surface, the skin of an airplane wing or the inside wall of a pipe. He realized that right at the wall, the fluid has to be essentially still because of friction with the surface. But a short distance away, it can be moving quite fast. So there is a thin layer right next to the wall, where the velocity changes from zero to fast over a very small distance. Prandtl called it the boundary layer. And here is what makes the boundary layer interesting. It is very often where turbulence starts. The steep gradient of velocity, the pile-up of motion right near the wall, is a ripe place for little instabilities to grow. Tiny irregularities in the wall, tiny imperfections in the flow, get amplified by the pressure differences, and soon you have eddies shedding off the surface and swimming out into the main stream. This was important for engineering. It meant, for instance, that the drag on an airplane wing was not just about the shape of the wing. It was about what was happening in that thin skin of air right next to it. And Prandtl's insight turned out to be a doorway into a whole practical way of thinking about turbulent flows. Not solving them, mind you, just finding useful approximations for specific geometries. But back to the main story. We are still hunting the mechanism. Now I want to tell you about a Russian. His name was Andrei Kolmogorov, and in the 1940s, during the war, working in the Soviet Union, he did something remarkable. He did not solve the turbulence problem. Nobody has solved the turbulence problem. But he did something that, in my book, is nearly as good. He found something true about turbulence, something reliable, something you could bet on, without solving the equations. Here is what Kolmogorov did. He said, forget about trying to predict every swirl. That is a losing game. Instead, let us ask a statistical question. On average, across lots of turbulent flow, how is the energy distributed among the different sizes of eddies? How much energy is in the big ones? How much in the medium ones? How much in the tiny ones? And he reasoned, in this cascade that Richardson described, the middle of the cascade ought to be fairly universal. The big eddies, those depend on whatever is stirring the fluid. The tiny eddies, those depend on how sticky the fluid is. But the middle range, where energy is just being handed down from one scale to the next, should not care much about the details at the top or the bottom. It should just depend on how fast energy is flowing through the cascade. From that argument, and it really is just an argument, he does not solve any equations, he predicted a specific mathematical relationship. The amount of energy carried by eddies of a given size should follow a particular rule. The rule has a number in it. The number is 5 divided by 3, Kolmogorov's 5/3 law. And here is the miracle. When people started measuring real turbulence, water tunnels, wind tunnels, eventually even the atmosphere and the ocean, they found the 5/3 law. Over and over again. The air mixing in a storm, water in a pipe, smoke in a chimney, hot gas in stars even. The 5/3 law holds.